Hi, how's it going? In this Mechanics of Materials, Mechanics of Solids video, I'm going to go through a brief look at Saint-Venant's principle and then also looking at axial deformation in an axially loaded component. All right, so let's have a look. This is just a screenshot taken from the textbook that we're using, so Hibbeler Mechanics of Materials, the 10th edition. And basically, Saint-Venant's principle says that it doesn't matter how the load gets applied, the stresses and strains that are developed some distance away from where the load is applied are independent of how that load gets applied. So we're around close to the load application region. So here at section AA, for example, so this section through here. All right, so here through section AA, if we look at the stress distribution, it's fairly intuitive that the stress is going to be higher near where the load is applied and less out towards the edges. But as we move away from where the load's applied, we'll see that these stresses begin to become more uniform. Okay, and the other way of thinking about Saint-Venant's principle is it doesn't matter whether we apply the load via one hole like this and have P, or whether we have two holes and the load is applied in half through the two loads here. So whether we have P or P over 2, doesn't matter. Around the loading area, of course, it will change, be different, but at some distance away from where the load's applied, then the stresses and strains are independent of the loading and also of the support. So you can see at the bottom of the picture on the left here, we've got a built-in support. If we had a pin connection at the end here, then the stresses and strains around that support will be different from a pin connection to a built-in connection, but at small distance away, they'll be uniform and independent of how that bar was supported. So the obvious question is, well, how far away do you need to be? And typically, if you're one width, so not the thickness, but one width away from where the loading is, then the variation in stress is less than 10% from the average stress. Okay, so that's pretty much it for Saint-Venant's principle. Now, yeah, the other thing, this is one very short section in a big textbook on mechanics of materials, and for the most part, through the rest of the textbook, this topic or this idea is pretty much ignored. Right? We just assume this without talking about it ever again. But when you go to do finite element analysis and stress simulation using finite element analysis, this becomes really important. And it really helps you to be able to simplify your modeling and to be able to interpret the stress and strain that you're seeing in your simulation. And without a good understanding of Saint-Venant's principle, you'll be often trying to model too much detail, or you may be looking at stresses that aren't real. Or you can say, all right, I want to know the stress over here, so it doesn't really matter if I apply the loads in a realistic way over here, as long as they're kinematically equivalent. We may look at finite element analysis a little bit later. For the meantime, you just need to be aware of it, and know that we pretty much gloss over it in textbook problems. But when you go to use finite element analysis, then you really must know this. We're going to now look at axial deformation. So in general, the strain within an axially loaded component may not be uniform. So we have to allow for that. So if we have a varying cross section, for example, then our strain is not going to be uniform throughout the length. Right, so if we now look at a small element or small length dx and say that we have a small change in length of that length dx, that small change is d delta, and here n are our internal normal forces. Okay, So at this section here, somewhere along the length of the bar or rod, we have internal normal force Nx, and by convention, outwards is positive, or pulling out from the surface is positive, or the element being in tension is positive. So that's what we have for our element. Now we know if the stress is uniform over this area, so if we're away from where the loads are applied, according to Saint-Venant's principle that we just looked at, then we can say that the stress is uniform over the area, and we can say stress is equal to the internal normal force over the cross-sectional area at some location X. If we're allowing for the fact that the stress or the cross-sectional area may change, the stress and strain may change throughout the length. And we know that the strain is equal to change in length over original length, but now we're just looking at this little small elemental or differential length dx here. Right? We're not looking at the whole length L because the strain is not uniform over the whole length. But over the small length dx, we can make the approximation or the simplification that the strain is uniform over this small length dx, and say strain is d delta over dx. Okay, so assuming that we're within the proportional limit and we can apply Hooke's law, so we can say here, right, this term on the right is equal to the stress, and from Hooke's law we have Young's modulus times the strain. So substituting Young's modulus into here and our strain into here, we get this expression for the change in length d delta of our little elemental length dx here. All right, so some of you might be starting to recognize what's coming. You might have seen an expression for this displacement delta, and we're going to get to that shortly. But if we want to know the change in length here, delta of the entire bar or rod that's loaded with these two forces here, then we need to integrate this expression, right, over the whole length. But if we have constant load and constant cross-sectional area, then we can take the normal force outside the integral because it's now constant. It's not a function of x anymore. We can take the area out the front of the integral because it's not a constant, it's not a function of x anymore. And if the material doesn't change through the length of the component, then we can take that out the front of the integral as well. So all we would be left with is integral dx. So adding up all of the little dx's that we saw in that previous diagram. So if we add up all of these little dx's, we get our total length L. Right. And then that leads to what might be a familiar equation for some of you. So the change in length of an axially loaded rod is NL over AE, or force times length over Young's modulus times area. Some of you may know this formula as split fleet, FL over EA, right? But that's only applicable if we have these conditions. The force or the stress doesn't change over the length, the area doesn't change over the length, and the material doesn't change over the length. Okay, so be careful about just applying equations that you've seen before and think, oh yeah, that's what I use, without really knowing the limitations of that equation. All right, what if we have multiple loads? Then we can just add up the displacements or the deformation for each part of the component. So just the sum of NL over AE. So we look at internal force for section L1 times its length over the area and the Young's modulus. Then we look at the internal force in section L2 here. So we need to do our method of sections like we did for stress. So imagine we take a cut through here, imagine we take a cut through here, and we work out the internal force. So previously I said when we calculate stress, try not to think about stress as force over area, where force is an external load like this P4 here. Rather, think of stress as N over A, where N is the internal normal force. When we're adding up our displacements, try to use a consistent sign convention. So our sign convention is that we consider both the force and the displacement to be positive if they cause tension and elongation. Whereas a negative force and displacement cause compression and contraction. So that's consistent with what we said before. So when you're drawing your free body diagram and calculating your internal action, probably a good idea to just draw the internal force always in tension. And then if you get a negative value, then you know it's in compression. All right, so that's it for that. Reasonably simple, but you need to make sure that you don't apply that equation NL over EA, where the force or the internal force is not uniform or the stress is not uniform, where the area changes over the length or the material changes over the length. All right, that's it for now. See you next time.